Welcome to the dSPACE learning series. Today I want to present you our BMS testing systems and show you how we can test BMS systems for electric vehicles with our software and hardware solutions. First, I will give you a short introduction into electrified vehicles and their BMS systems, and then I will show you a live demo of our system here that we have here. The main purpose of this seminar is to realize some key takeaways when it comes to BMS hill testing. Our dSPACE hill concepts using flexible and extendable simulator design apply safety features and integrate our ASM battery models as well. Our new cell simulation hardware is providing outstanding performance in voltage and current range and accuracy for up to 1500 volts. And our integrated ASM models are built in to be a complete BMS test system. If we are looking at a typical system approach for an electric vehicle, we see a mixture of components: inverters, batteries, motors, and actuators. But most of the challenge portion of the system is going to be the traction system, because it uses high voltage and high power components to move the vehicle. The central component of this system is the battery and the battery management system. And today I will show you how to test this crucial part of the electric vehicle. If we are looking at high voltage batteries, they generally power the propulsion system of an electric vehicle. The battery pack makes up a significant cost of the vehicle and is characterized by their relatively high energy density. The state of charge for the battery needs to be controlled in a 20 to 90% window, which often means that the BMS controller needs to adjust the cell voltages within just a few millivolts. Battery packs come in all sizes, shapes, and forms, with DC voltages reaching over 1000 volts. They are designed for a large number of charging and discharging cycles and are modular, scalable, and highly integrated into the vehicle chassis. dSPACE BMS test systems are designed to cover all the design and performance specifications of these BMS systems. The battery management system has to handle a lot of different tasks: voltage and temperature measurement on cell and stack level, overall current measurement, thermal management, as well as operating relays and safety routines. The battery management system also calculates the state of charge, the state of health, and often monitors the insulation resistance between the high voltage bus and the rest of the vehicle. The cell supervision circuits, or cell monitoring modules, measure the cell voltage in the microvolt range, as well as temperatures of the individual cells at a high voltage level. The CSC will also control the active or passive cell balancing. When we want to test the BMS system with a hardware-in-the-loop simulator, there are different use cases to set up the system. On the voltage level, the BMS and CSC controllers are real components connected to the HRL system, which is running a simulation of the battery system. Testing the system on a signal level means that the CSC modules are also simulated in the hill itself. Then the communication between the BMS and the CSC modules is simulated in the system itself. Depending on the hill setup, this communication can be based on different protocols like CAN, SPI, or others. Taking a closer look, we'll see that with signal level simulation, the hill system simulates the interface between the CSC and the BMS, and therefore doesn't need specialty hardware to produce individual cell voltages. When we move to high voltage level testing, the CSC module is a real component in the system, and the simulator needs to provide a real cell voltage based on the battery model. Simulation on a high voltage level also has other challenges. The cell voltages have to be provided by the simulator with a very high accuracy, down to the millivolts. Galvanic isolation is required to separate high voltage components from the rest of the system. Often high voltage power sources are required for overall battery simulation. And the temperature sensors have to be simulated by isolated outputs as well, because they're part of the high voltage system in the battery itself. And since we can provide battery stack simulation for up to 1500 volts, We also add safety features to the system to provide a safe environment for the testing system itself. The Scalexio Battery Hill system is designed to test BMS system on a high voltage level. Using our Scalexio real-time technology as a base for the system, we're using our real-time hardware with flexible and expandable I/O capability. We use specialty hardware for high voltage operations and cell simulation. We can use our common dSPACE user interface with our standard softwares, control desk, model desk, or automation desk, and with our ready-to-use ASM battery model, which is designed to integrate with our hardware, we're providing a complete package from one stop. Taking a closer look at a typical BMS cell setup, the system includes several components to simulate the battery system to the BMS controller. We have a large safety compartment for the cell simulation boards and the BMS and CSC modules. We also have high voltage power supplies that we use to simulate the pack and link voltages in the system. We're using low voltage power supplies for controller supplies and other parts of the overall vehicle. And of course, our Scalexio real-time system to execute the vehicle and battery models in real time. BMS Hill systems can be customized for different applications, from small integrated systems to multi-rack applications with simulation of battery stacks, including hundreds of cells. I also want to point out some of the integrated safety features of our systems, since we have voltages that can go over 1,000 volts, and we want to make sure that the system is safe to operate. As mentioned earlier, we have a safety compartment that will house the BMS and CSC controllers, as well as all high voltage components. All high voltage is staying inside these components. If the door is open during operations, the high voltage will be automatically disabled. We also often integrate isolation monitors into the system to make sure that the high voltage is properly isolated from the rest of the rack. Inside the simulator itself, the high voltage wiring and components are clearly marked and protected against unintentional touch to add a second layer of safety. The safety signal on top of the simulator provides a clear indication of the status of the Hill system, as I will later show in the demo as well. Additional features of our BMS Hill simulators, as I mentioned before, they are scalable from small to large system. They are fully customizable and integrated into our existing Scalexio real-time toolchain. They can be used for a wide area of applications, from battery vehicles to stationary storage systems. We can emulate voltages up to 1500 volts. We have a low latency real-time connection to our Scalexio systems, which helps us to execute the battery models at a high rate. And we have a best-in-class cell voltage emulation with a high precision voltage output and currents up to 20 amps. At the heart of the BMS simulators is the battery cell simulation. We have been providing our customers with BMS Hills and cell simulations for more than 10 years. And last year, we introduced the next generation of cell emulation hardware. Based on a sub-rack design, the new cell emulation hardware was developed with a new system concept in mind. It's a modular system that can be scaled from small to large systems. The sub-rack, as you see in the picture, can be fully integrated into the safety compartment of any Hill simulator that we customize and build. This will allow for short wiring from the test system to the actual control modules, and also provides easy access for maintenance and calibration. With the current design, we can fit up to 60 modules in every sub-rack. And with the 2-channel high-end cell emulation board that we have right now, we can provide a sub-rack with 32 cells of cell simulation per sub-rack for your development. This system is also prepared for the future. So we can add expansion boards for this. For example, we're working on a high voltage supply board that will be part of the system as well. The complete new rack design is also prepared for all needs in the fields of BMS testing. As I mentioned, up to 32 cell voltage simulation channels can be added to one rack. It's also designed to carry temperature simulation boards, insulation failure boards, and high voltage sources. And with an FPGA interface board, we are able to execute battery models even faster than the future, even doing on the FPGA board itself. And again, this system is very easily scalable for like a high cell count system. At the center of the new BMS hardware is our new cell emulation board. With a maximum system voltage of 1500 volts and high accuracy on output voltage and current, this board is able to cover all current and future vehicle battery systems. The high output current per channel with 5 amps continuously and over 20 amps peak makes it ideal for testing cell balancing strategies in your system as well. Diving a little bit deeper into the new cell boards, we'll see the basic function groups of the new solution. The cell voltage generator and the high current output provide the base of the system. They are connected directly to the application running in the real-time system, and so based on the battery model, it will send the individual cell voltages and currents directly to this board. The voltage and current feedback will also report the actual measurements on the DC link back to the ASM model. We do have a voltage feedback as well as a 2-level current feedback to be able to measure current in the milliamp range as well in the amp range. The FIU portion of the system allows for mechanical interruption of the cell and therefore to be able to test certain FIU strategies you have on your controller. Each board has 2 channels for cell emulation, and we already included internal connections that makes it easier to put stacks of cell boards together. So whatever your battery's configuration is, we can provide a system that provides multiple boards for battery simulation. Comparing the newest generation cell emulation with our first generation, we can clearly see that there's an evolution of specifications. The overall maximum voltage was increased to 1500 volts, which will allow us to design BMS test systems for all types of user applications. The accuracy of the voltage and the current controller has also been improved significantly. The interface to the real-time model is also faster than the previous generation boards. With the battery model running on a Scalexo processor, we can achieve update rates of 5 to 50 microseconds for our battery models. And since the interface now is based on our FPGA technology, we will be able to run even faster battery models on the FPGA boards itself in the future. The second board of the new generation hardware is our temperature emulation board. This board can also be integrated into the BMS subracks and provides 8 resistive channels for temperature simulation. So you can mix and match in each of the subracks between cell emulation and temperature emulation to come up with the best solution for your testing needs. This board is also has a galvanic isolation of 1500 volts, so we can use it for the same application as the battery emulation board. We also have a very fast interface to our battery model. At about 100 microseconds, we can execute, these temperature emulations on the board itself. And of course, we will continue to expand our portfolio of solutions for BMS simulations in the future. Right now, we're working on a 4-channel cell voltage emulation board. This board will allow us to add up to 64 channels per subrack for an even higher level of integration. We're also working on a high voltage emulation board. This board will allow us to put a high voltage power source into the BMS subrack and therefore make it easier to put a system together and reduce the overall wiring effort of the rack system. On the signal level, we're also working on expanding our solutions for ISO-SPI. So we will have expanded capability for different chip types in the future. And lastly, we're working on pre-configured BMS test systems. These these test systems will have a wide variety of pre-configured specifications. And the advantage is that if we have these in place, we can expedite the delivery of these systems because there's less customization and less custom wiring on these systems. The tried and tested ASM multi-cell battery model is really the center of our modeling strategy for BMS test systems. The model can test or simulate the performance of any type of battery systems for any type of application. The ASM battery model simulates the voltage behavior of a battery based on an equivalent system with two RC elements as a default. The battery pack respects cell-wise balancing currents and can handle each cell temperature while simulating the voltage behavior of the battery. The battery pack topology varies from application to application, and the ASM battery model follows this flexible approach. The system can be formed with a parallel connection of battery packs, which contains a flexible number of series connections of battery stacks, where each stack represents a parallel connection of battery cells. Whether or not a clustering of modules is needed depends on the architecture of your battery. The library also contains a very comprehensive ready-to-use demo to shorten your time to get to testing. And of course, the real-time capability of the demo is ensured. So we working directly with our BMS Hill hardware to provide you a complete BMS Hill test system. The ASM electric battery model is providing a variety of outputs to the overall system itself. So we're calculating the terminal voltage based on ohmic losses and dynamic behavior. We are doing a cell-wise state of charge calculation, also respecting balancing circuits in the system. We calculate a thermal model with temperature simulation for each individual cells. We have a variety of battery types that we are supporting with this library, all the way from lead acid to lithium-ion batteries, depending on the parameterization. We can also add other components of the electrical vehicle system into the model itself, like pre-charging circuits or DC link or a charging station. Again, with a ready-to-use demo, which is included in the ASM library, we're adding a soft ECU that intuitively coupling the ASM library, to your vehicle plant model, and therefore you can start your implementation faster. And again, we're providing with our library a direct support of dSPACE cell voltage emulation hardware. Like all our ASM models, the ASM battery model is defined by parameters that need to be specified. This will allow the battery model to behave very closely to the actual battery for a realistic simulation. So we're setting things like battery types, capacity, cell voltages depending on the state of charge, and some other components that we want to make sure we have in the simulation to be as closely as possible to the actual battery that you're using. For the model architecture, as I mentioned earlier, we are very flexible in the topology of the model to be able to cover the flexibility of battery topologies that are out there. So we usually talk about a battery system, which forms the final battery, a battery pack, which is a unit controlled by a BMS module, as a unit clustered by a CSC. The stack is usually considered a parallel connection of equal cells. And then also, we do have some, topologies, the number of cells in the stack that we can adapt to whatever the actual battery is. For example, a 6x4 pack configuration by a stack of 6 cells in parallel and 4 stacks in series to form a pack. We also use this topology to do the thermal analysis of the pack, and of course to create a realistic representation of the voltages. The ASM battery model will also calculate the thermal behavior of the battery pack. The heat generation is determined by internal losses, the chemical reaction, heat flux, and other parameters. The temperature is simulated for each cell, and the thermal interaction of neighboring cells is also being considered. This, of course, is based on the battery stack configuration and the geometry as well. The ASM battery library also includes the ASM BMS demo. This is a new portion of the library that we just introduced. So we added a new BMS soft ECU and an improved battery simulation that you can use together to run your system. And again, with all of our ASM libraries, as you know, you can use our current software toolchain and dSPACE softwares for that, using Model-DESP to parameterize your system, using Control Desk to interact with your whole system, and using automation tests if you have to do any type of test automation. So this means like less effort, and you can also do a lot of test preparation in the virtual world before you actually go into the Hill system itself. dSPACE also offers additional ASM libraries that are specifically designed for electrified drivetrains. The ASM electric components libraries includes components like starters, alternators, electric loads to simulate the vehicle electrical system, as well as electric drive components like fuel cells, motors, and inverters. These can be done for closed-loop simulation of power electronics, as well as implementing a simulation of your full vehicle. So when it comes to BMS test systems, dSPACE offers a hardware and software solution to cover the complete range of test applications. For a signal-level simulation, our Scalexo real-time hardware can be used to simulate the system, including the cell monitoring models. So we're really focusing on the communication between the BMS and the Hill system. As I mentioned earlier, mostly CAN, SPI, or ISO-SPI. When we're switching to a higher voltage simulation, our high-precision cell emulation boards, together with our flexible Hill system, provide you a safe environment to test your BMS system under high-voltage conditions. On the software side, our ASM models provide a ready-to-use Simulink model interface that is designed to run in real time and is directly integrated with our hardware, so that it's really a very seamless solution to use software and hardware together to get your BMS testing done. Hopefully, I was able to point out some key points when it comes out to solutions for our BMS testing. As I mentioned earlier, we're providing a sophisticated Hill concept using a flexible and extendable simulator design, which applied and integrated safety features. Our new cell simulation hardware is providing outstanding performance in voltage and current range and accuracy for up to 1500 volts. And of course, our integrated ASM models build the simulation backbone for a complete BMS test system. And now let's take a look at the live demo. For the second part of the webinar, I would like to show you our BMS demo system in action. So this consists of a hardware HRL system plus the software we're running on the screens on the side. So this BMS demo system incorporates all relevant components that I mentioned in the presentation earlier on. On the bottom, we have our safety compartment, which includes the BMS subrack, which has the cell simulation boards in it. In this particular case, we're using 3 cell simulation boards, which is able to simulate 6 cells for the device under test. The device under test is probably hard to see, but it's an integrated BMS controller that does also the cell monitoring in one board. On the second level here, we have 2 power supplies. We have a low voltage power supply that is used to power up controllers and any other parts of the system. We also have a high voltage power supply that can be used to simulate the link voltage or the battery voltage of the battery system itself. We also have an isolation monitor here that makes sure that the high voltage is always separated from the rest of the system to make sure we have a safe operation of the system itself. Behind this plate, there's our Scalexo real-time system, which you cannot see right now, but the system is the one that's executing our real-time application and controls all aspects of the system here as well. On top here, we have what we call our power distribution subunit. This one has the main power switch and e-stop switch for safe operation. which is unique for a BMS system is that it has a secondary circuit for all high voltage components. So we're keeping the high voltage and the low voltage very much separate to be able to ensure safe operation of the system itself. And on top, we do have our signal light that will indicate from afar what the status of the system is. In the moment, this system is fully operational under high voltage, which means the green and the yellow light are on. And just for monitoring what the actual device under test is doing, we have a tablet here that is running and basically showing us what the controller is actually seeing from the simulation of the test itself. So this kind of like shows you what an overall BMS system should look like. Again, this is really just a small demo system. We can also scale these systems up to hundreds of cells and multiple racks as well. So moving over to the software side, I mentioned earlier that we are running our ASM battery model in this particular demonstration system. Looking on the right here, we'll see a representation of the ASM model. With all our ASM models, these are based on MATLAB Simulink. They are open models, so you can dive in and you can figure out where we are calculating state of charge or voltages, or you can also insert your own pieces of model if you find that you need to put in your own touch to that. But with all ASM models, these are open. There are no black box models, and we are able to integrate this in our system as well. Also, since the ASM battery model is a very generic model, we need to specify the parameters of the model itself to basically make sure that the controller that is sitting in the hardware recognizes that as a battery. In our case, we're using a 6-cell simulation model, so we have to configure the battery as a 6-cell battery in order for the controller to work correctly. The easiest way for all of our ASM libraries to be parameterized and configured is to use our tool called ModelDesk. ModelDesk will give you a very nice GUI interface to where you are able to put in all the parameters of your system, and it will automatically download these parameters into the MATLAB Simulink model, so you have the exact representation of the battery you want to model in your system. Again, we're doing a 6-cell model here, as a simple stack, only one row, 6 cells. We can also add parameters for the state of charge. We can put in parameters for voltages and battery resistance. So really, every parameter that you need in order to configure your battery model can be done through this ModelDesk interface. And again, it is an open MATLAB Simulink model. So once the model is being parameterized and compiled, we'll move it over into the real-time system where it will be executed in real time. And then we'll interact with the model and the hardware through our tool control desk. All right, moving to the left side of the screens, we have control desk running. Control desk is our software that interacts directly with the hardware running on the BMS system itself. So with control desk, you can have different layouts for different purposes. The first one I'm showing here is our generic simulation control layout. With this layout, we can change the voltages of the power supplies. We can interact with the actual cell simulation hardware itself. And we can also, set up some failure conditions if you wanted to test those as well. If you're looking into more of like what the battery simulation is doing, we have this screen here which shows our 6 cells, basically in a setup. And right now we're running an automatic demo. So basically we are switching between driving and charging cycles to show like the charging and discharging of the overall battery pack. You can see here like that by default we have set the statement of charge in some different ways to show you some differences here. We're also showing you some balancing current, which there's none going on right now, but in a minute I will show you how the balancing current will increase once we start that process. You can also see here, which is probably hard to see, but there's some minimal current running from the cells, which is different from the overall simulated current. This is actually current that is being run to the actual controller because the controller is powered by the cell voltage itself. So the controller we're having here does not have an external power supply. It uses the cell voltage as its own power supply. So if you're looking at this, as I mentioned, we're running an automated test. If I'm switching this turn this off and basically move to a charging cycle only, you will see that the state of charge will increase, that at some point in time the controller will recognize that the state of charge of the different cells are in different values and will activate the balancing algorithms and started to move current between different cells. So this should happen here in a moment, and you will see then that the balancing current will show how the current will move between different cells. Let's wait for a second here. It should happen any moment, really. I know you can see here that the charging current, the balancing current is activated. This controller does a pulsing of current, so it can probably control the state of charge better. But in general, you can we simulate this, and the feedback from the hardware then goes feedback into the ASM model to then calculate the new states of charge as well. If I go back and turn on the automatic demo again, you will see that then we're starting the discharging cycle again, basically the drive cycle, getting power out of the battery, and at some point in time the balancing current will also disappear. The other layout I wanted to show you is basically one that is specifically designed for the actual cell emulation. So we have really a very close look at how do we interface with the cell emulation boards. So as you can see, the model is providing right now the individual cell voltages. We can also read back the actual cell voltages that we are reading directly from the hardware. This one also gives us the opportunity to basically overwrite the voltages or the signals from the model itself. So if you want to test out how your controller reacts, let's say if one of the cells goes blank or has an overrun, you can do this here as well. We can also add our failure simulation here because we have to have a broken wire capability in the system. So you can enact the failure here as well. So again, control desk is the one where you interact with the hardware running. And obviously with all our dSPACE software tools, you can also use test automation and automation desk to automate some of these things that to automate the interaction with the system. If you have a test plan, if you have certain test requirements you want to hit, you can do this automatically without sitting here and clicking these different signals. I also want to show you that safety is an integral part of our BMS system. So if I'm going over here again and looking at the safety compartment, right now, as you can see, the high voltage is activated. The battery voltage, the battery simulation is activated, and the signal light indicates that the system is operational and running. If I'm open the door, you will notice that the signal lamp went to red, indicating that somebody has opened the safety compartment. The power of the cell simulation was turned off to make sure that there's no high voltage in the safety compartment anymore. We also turned off the high voltage power supply, so we don't have really anything high voltage in the system anymore. If we're going back to closing the compartment, now we are able to turn on the high voltage power again. This is not done automatically. So basically you have to do this by hand here with the secondary circuit I mentioned earlier. This makes sure that you don't inadvertently introduce the high voltage to the system again, so it has to be an active movement. So if I turn this on again, you will see that the cell simulation boards are coming on again. The high voltage power supply is going back to the set value, and the system is up and running again. Safety is very important to us, so having the high voltage contained in the safety compartment, having the high voltage components being separated inside the system with a secondary safety circuit makes sure that we have always a safe system to operate, and that is really why we're doing these specific safety features on our BMS systems. So this concludes my demonstration of our BMS Hill system. Thank you for joining us, and if you have any questions, we'll be available to answer any questions you might have. Thanks everybody for listening. I really appreciate you stopping by and listening to what we have to say. And again, if you have any more questions, then just reach out to us and we're more than happy to discuss BMS test systems in more detail.
dSPACE, your partner in simulation and validation.